Okay, so we have either 1 or 2 or 3 rare Pokemon cards in a pack, and we are told this is the information. So we are 6 times more likely that it contains only 1 rare card than it contains 3 rare cards, and it is 3 times more likely that it contains 2 rare cards than it contains 3 rare cards. So this is a little cryptic. There's a lot of numbers floating around, but if you have the right way to put this in your brain, this is a very nice thing to do. The way I like to think about it is a number line. Let's draw a little number line. Where's my blackboard? Here it is. And let's make a new page. So we can either have here, here's 1 or 2 or 3, and we're going to make the random variable x is the number of rare cards we get, and it's either 1 or 2 or 3. And you can think of sort of the various probabilities of getting either 1 or 2 or 3 as kind of being little stacked weights. So you say there's some probability over here. So I'm drawing on the y-axis. I'm drawing the probability of each outcome. And if we decode this little thing, what is it saying? You are 6 times more likely to get 1 rare card than 3 rare cards. So what this is saying is the relative heights of the little stack at x equals 1, it should be 6 times taller than the other one. Let me see if I'm going to run a room here. 3, 4. Okay, we're gonna have to move the label because it's in our way. 5, 6. So in other words, this one is 6 times taller. Whatever height that this one is, that one is 6 times taller. Okay, and similarly with the other one, in the middle, it is 3 times more likely it contains 2 rare cards than it contains 3 rare cards. So we can draw this one. It's going to be height 3. So we don't actually know the individual heights of these things, but we do know they kind of relatively stack up like this. This is kind of a histogram. And again, we don't know what probability this is yet, but we know that whatever it is, this one is 3 times taller than that one. This one is 6 times taller than that one. So this really is a graph of the function, what we call P of x, right? Where this is the probability mass function, the probability that x equals x, and we're told the relative amounts of it. So that's how I would think about this little cryptic information for x is the number of rare cards. Let's fix this definition up now that I've erased part of it. Okay. So that's what I did and how I thought about it. And then that leads you to trying to get an intuitive sense of the average. Is the average between 2 and 3, or is the average between 1 and 2? And let's see what people said for that. Okay, let's start with this one. The average is between 1 and 2, overwhelmingly popular and exactly correct. So you can kind of tell just by looking at this little graph, even without calculating anything, that the average has got to be somewhere between 1 and 2. The average you can think of as where you would have to balance this, the balancing point. And I think it's somewhere here. So if you imagine there were weights, like a little I don't know, how much does a pack weigh? 100-gram weight on each of these. The balancing point is somewhere here, where this stuff all balances with this stuff. In fact, actually, if it was 50-50, if I had, five weights at 1, so this is an alternate universe. If I had 5 weights at x equals 1 and 5 weights at x equals 2, so let me draw the 5 weights at each of these, then it would be exactly at the mean. The average would be exactly at the middle, 1.5. So if I had 5 and 5, it would be exactly at 1.5. I don't have 5 and 5. I have 6 and 3 and 1. So kind of 1 has moved over here, but it's pretty similar to that situation. So I would say the average is going to be like a hair more than 1.5 because this 3 is going to pull up the average. Although there's an extra weight at 1 that's going to pull down the average. So it's going to be right around 1.5 just by intuition. So just looking at it, must be close to 1.5. Must be around 1.5. Okay, so that's the kind of thing you can intuit. We're going to calculate it exactly in a second, but just based on the picture, we can get the intuition. Yeah, I think sometimes people get lost in the sauce of calculating averages and they forget they're kind of intuitive. Like they're not supposed to be some crazy complicated formula. The formulas are supposed to help you understand this kind of thing exactly. Okay, so that was very well done. Almost everyone got that right. here is where we start to get into the actual calculation, right? This is the intuition. Now we're going to exactly calculate. And to exactly calculate, we do need to know the actual probabilities. What is the probability contains exactly 3 rare cards? And let's see what people said. Okay, lots of people have no idea how to do this. Some people said 0.1, lots of other possible answers. 0.055, that's interesting. What is that, like 1/11th or something? 1/11th maybe? Maybe not. Okay, well, whatever it is. So lots of different answers. Let's take a look and see how we would do it. And the way I would do it is you could just count up the boxes. So how many boxes are there? There's 6 boxes here. Okay, this is, let's write down what we're doing. Solve for the probability x equals 3. And I'm going to do method 1, which is like the baby method of counting boxes. Okay, in this case, there were 6 boxes over here, right? Because group 1 was 6 times bigger than this, and there's 1 box over here, and there's 3 boxes over here. And therefore, there are 10 total boxes. There are 6 plus 3 plus 1 total boxes. And each box, again, remember, represents some amount of probability, and we did 6 and 1 to represent the fact that this one was 6 times bigger than that one. So there's 10 total boxes, and if there are 10 total boxes, how big is each total box? Since all boxes together must be 100%, if all the boxes together are 100% and there's 10 total boxes, therefore each box is 100% divided by 10, which is 10%. And that's 0.1. So that 0.1 is the right answer, which I think was the most common sort of answer over here. So very nice, very nicely done if you put 0.1. I will say, in addition to doing it the sort of counting way, you can also do it with algebra. That will do the same thing. And the algebra is really a fancy version of the counting boxes. This is algebra. So I don't know, what should we call it? Let's call it Q. We've used Q for probabilities. Let Q equal the probability that x equals 3. Then we see the probability x equals 1 is 6Q, and the probability x equals 2 is 3Q. So total probability is 6Q plus 3Q plus 1Q. So in fact, the algebra way is to just, instead of calling it a box, give the box a name. And I called it Q, but we're really just counting up the number of Qs we have. We have 6 plus 3 plus 1. And so we get the equation, this is 100%, and therefore Q equals 10%. So the algebra way is really identical to the counting boxes way. It's just one is a little bit more intuitive than the other. The nice thing is the algebra way, you can work with more cryptic information, right? Algebra lets you do all these fancy calculations. They don't have to be whole numbers anymore, and you can still work it out. Okay, so that is calculating the probability. Last but not least, I want to calculate the average, and I'll do that in 1 second. But maybe this is a good place to pause for questions, because I did those somewhat quickly. Let's open this back up. Okay, so we took the information, we turned it into these 6, 3, 1 situations, and now, last but not least, I'm going to calculate the average. But any questions or comments about what's going on so far? Yeah. Yeah, I think there's 3 events. There's the probability. There's x equals 1. That's one event. You open the pack and there's 1. There's x equals 2. That's another event. And there's x equals 3. Whenever you have a random variable, all the different values it can take on, those are all events. That's right. No, the way we did it is the way you have to do it. Yeah. Yes. Well, so the thing is, in the question, we were not told the exact. Maybe there's a different question in a different problem where we're told the probabilities. But in this question, we were not told the exact probabilities. We were told the relative sizes of the probabilities. We were told this one is 6 times more likely than this one. And we used that. We combined the information that was given with the fact that all of the events together have to be 100%. And that is how we calculated the probability for 3 rare cards. And by the way, once you know the probability for 3 rare cards, you know the probability for 1 and 2 because you multiply them by 6 and 3. So the way we did it is we took the information that was given and we calculated what we needed to calculate. Yeah, that's a great way of thinking about it. Any other questions or comments? Okay, so next up, I will calculate the average. The average. Calculate the average. The average, I like to write it as the expected value because you're going to see that depending on how you think about the average, it might be the straight arithmetic mean, it might be the weighted mean, but if you say the expected value, it's very unambiguous what you mean. Plus, there's an extra bonus, which expected value has a nice acronym that some people use called the EV, which is something we saw in class on Friday, the EV. So that's quite nice. So what are the 2 ways? I think there's 2 ways you can do it. You can do it based on events, or you can do it based on outcomes. And if you remember, the difference is, it's just what do you group together. So the events, there are 3 events here. There's x equals 1, x equals 2, and x equals 3. Probability x equals 1, the probability x equals 2, and the probability x equals 3. And those are the 3 outcomes. So to calculate the expected value with the events, you use the formula that we talked about in the video, and we're going to review again today. We're going to use the formula, the expected value of some random variable x. It's equal to, in this case, it's 1 times the probability x equals 1 plus 2 times the probability x equals 2 plus 3 times the probability x equals 3. In general, it is the sum over all the possible values. So it's the sum over x, and then you do lowercase x times the probability x equals x. So some people call this the law of the unconscious statistician, which I think is very funny. Unconscious statistician. But that's if you want to Google this thing, that's what it's called. And it says you go over all the possible values and you multiply the probability times the value. So you're doing a weighted average of these 3 values. In our case, so we're going to do 1 times this, plus 2 times this, plus 3 times this, and that is equal to 1 times 6 over 10 plus 2 times 3 over 10 plus 3 times 1 over 10. So we have the 6 over 10, 3 over 10, and 1 over 10 from our first part, and we're doing the weighted average of these 3 numbers. This one is weighted by 1, this one is weighted by 2, and this one is weighted by 3. That's not what I meant to say. We're doing the weighted average of the numbers 1, 2, and 3, and we're weighting it so 1 is the most likely, 2 is the next most likely, and 3 is the rarest. So in other words, it's the average of the numbers 1, 2, and 3, but they're weighted by how big they are. This one weighs the most, this one weighs the second most, this one weighs the least. So that's why, the intuition we had, it's got to be around 1.5. That's why it makes sense. And in this case, what do you get? You get some number of tenths. 6. Oh, this is a 6 plus 2 times 3 is another 6. And then plus a 3 over 10 from the last situation. So that's 15 over 10. Hey, look at that. It's exactly 1.5. Wow. What an amazing coincidence. 1.5. So that's based on events. Almost always you'll do it this way. If you have the actual probabilities, this is the most useful formula. There is another way you can do it that is totally equivalent that I want to briefly say, which is to go based on outcomes. And in this case, you can kind of imagine that each box is an outcome. There's 10 outcomes. You could either be in this one. There's 6 ways you could be in this one. There's 3 ways you can be in this one. And there's 1 way you can be in that one. Sometimes it's more useful to go based on outcomes. And in this situation, all outcomes have probability 1/10. So this is maybe like rarer. This is a rare solution or an uncommon solution. But in this case, what you would say is there are 10 outcomes. They are all equally likely. So each outcome has probability 1/10. And what are we doing? We're doing 1 6 times. So we're doing 1 plus 1 plus 1 plus 1 plus 1 plus 1. There's 6 times it was a 1. There are 3 times it is a 2. And there are 1 time it is a 3. What this is kind of saying is that if you bought 10 booster packs, 6 of your booster packs would have 1 rare card, 3 of your booster packs would have 2 rare cards, and 1 of your booster packs would have 3 rare cards. So after you bought 10 copies of the booster packs, then this is kind of what you would get on average. You would get 6 1s, 1 plus 1 plus 1 plus 1, 3 2s, 2 plus 2 plus 2, and 1 3. And so what was the average number of cards? Well, you divide that by the total number of things, and you would divide it like that. And if you look carefully, this is exactly the same as the calculation we did over here. So the law of the unconscious statistician says just group all these together into one event and say it has chance 6 out of 10. Here we're adding them up individually. Sometimes that is more useful. It should work out to the same number, 1.5, because it's exactly the same math. Just 2 different ways of thinking about it. And this one is a straight arithmetic mean. It's the arithmetic mean of the numbers 1 copied 6 times, 2 copied 3 times, and 3 copied 1 time. Whereas this one is sort of a weighted average of these things. So there's 2 different ways of thinking about the same conclusion. Any questions or comments about that? Yeah. Right. Yes, that's right. Yeah. So it's saying out of all, imagine that there are 10 booster packs in front of you. 6 of them have 1, 3 of them have 2, and 1 of them has 3. And we're adding up together. And we open up all these 10 packs. How many will we get? That's the total. And this way is exactly the same, the law of the unconscious statistician. It's just that we have grouped them together. We've said there's a 6 out of 10 chance of getting 1, and so on. But the math is identical either way. And sometimes it's helpful to know both ways of thinking about it. Sometimes it makes it a little bit easier to think about this way, and a lot of times it's easier to calculate this way. So it's good to know both. Absolutely. OK. Any other questions or comments? OK. I think that is it for the warm-up question. It's funny that it worked out to exactly 1.5. I think I didn't want to make it exactly 1.5, but I guess that's how it came out. That's cute. Unless did I do the math wrong? OK, no, it's fine. All right. Yes. Any comments about this one, Professor Humphrey? No. OK. Let's do another one. We have a few more, and yeah. So this law of the unconscious statistician is the main way we'll be calculating averages. And it's one you absolutely need to know for all sorts of problems coming up.
Actually, I can make a comment. So you had 6 boxes on the 1, 3 on the 2, and 2 on the 3. We could imagine what would happen if we took the 2 on the, or the 1 on the 3 and put it on top of the 2.
So yeah, you want to do like a thought experiment. If I put this over here.
You put over that, and in that situation, you would see that that clearly isn't going to balance at 1.5 because the weight on the 1, which is equally distant from the weight on the 2, it would be pulled on the 1. And so moving the 2, one of those boxes over to the 3 gives more pull on the lever there.
Yeah.
So that it balances at 1.5.
Well, yeah, this is, so I think we could do 2 operations. We could do one operation of moving the box on the 3 over to the 2, and we could move one of the boxes from the 1 over to the 2. And by doing so, you've sort of done an equal amount of movement. You've moved 1 unit of mass to the left 1 unit, and you've moved 1 unit of mass right 1 unit. And so sort of the average should not change. This is sort of a fair trade. Moving the orange box over 1 to the left and moving the blue box over 1 to the right is a fair trade. It should not change where the average is. And once you do this, you'll see that it's exactly equally stacked. There's 5 boxes on the 1 left, and then now there were 3 boxes on the 2, but we've moved 2 boxes in. There's also 5 boxes on the 2. So after this operation, the average was 1.5, and because the average hasn't changed, it must have been 1.5 to begin with. So this is kind of like a tricky way to get the answer. That is, maybe not so straightforward. But of course, if you can calculate it, this is the nice thing about calculating. You can just calculate and see that it's 1.5 without any trickiness if you want. All right, okay. Maybe we should move on to another problem.
We can move on to another problem.
All right, let's move on.
On to another problem. Okay. Okay, so there's no pre-post on these slides because I kind of didn't want to pre-post these ones, so we will get a post on these. following up on Professor Nika's stuff, we're going to give you a few formal definitions. Let's just start with this particular probability distribution. And there's 4 possible values for x. X equals 1, 2, 3, or 4. If you want to have something to imagine, you might imagine that what we're doing is looking at the number of eggs in bird nests of a particular species. And then if we look in those bird nests, we either see 1, 2, 3, or 4. We don't count the nests that have got nothing in them. We're looking for ones that have eggs in them. And just to make it a little bit of an extra challenge there, we can tell you that there's a 20% chance that we'll find 4 eggs in the nest. There's a 50% chance that we'll find 3 eggs in the nest. And we didn't tell you what percentage of the time you get 1 egg or 2 eggs in the nest, but what we can tell you is it's twice as likely to get 2 eggs in the nest as 1 egg in the nest. So what we're going to do is work out the expected value, variance, and standard deviation of x. A couple of these things we have yet to define. But our very first thing we need to do is start off with, what the heck is the value of c? Okay, start off with the value of c. Now, we'll let you just solve that on your own for the next 12.3 seconds. And the very first thing you're going to start off with is say to yourself, well, for this to be a probability distribution, the sum of the probabilities have to be 1. Right? And then, like lightning, you've probably solved what C is. And if you think you know what C is, put your hand up, and I will whisper whether you are right or wrong. What do you think? Okay. Dead on. Dead on. Dead on.
I will say this is a great kind of midterm problem, because if you know what's going on, it's very quick to calculate what is C. It's very easy if you know what's going on. And if you don't know what's going on, if you haven't studied or you don't know what random variables are, I think it's basically impossible to calculate C. So it's a great litmus test. Do you know what's going on if you can calculate C? All right, what is it? Let's get the solution.
Okay. So a very quick solution here. Let me see, dot camera. Give me a dot camera here. We'll just recall.
Oh, it's very zoomed in.
It's very zoomed in. Okay, I'll zoom out. I'll zoom out. Okay, I'll zoom out. Okay, so it's there. Recall the summation of p of x is equal to 1. I haven't written everything out here because if it says it's a probability distribution, and if it's a probability distribution, the sum of the probabilities has to be equal to 1. So we know that. So what have we got? We've got c plus 2c plus 0.50 plus 0.20 equals 1. Let's see, that's 3c plus 0.70 equals 1. 3c equals 0.30. C equals 0.10. Okay, so we've solved for our C. So at this point, we're going to start with just simplifying our table a little bit. And so then we're starting with again, you can verify that those sum to 1. Always a good check. Okay, so we got that, sum of 1. So now let's find the expected value. We'll start off with the expected value. And Professor Nika has already defined the expected value. I'll just redefine it on a slide. You're going to see this. And what we saw here is the expected value of of a discrete random variable. Okay, so later on we're going to be doing continuous random variables. We're not going to be doing them before the next test, but we will be doing those after the next test, continuous random variables. Actually, that just reminds me of something to mention about that next test. What, you want it today? No, we can't do it that fast. No, that's good. We've got it scheduled November 5th, right? November 5th. It's on your announcements, the room, which is the same as last time, which was McNaughton 113. And double check the time. Was it 7 or 7:30? I think it's 7. And we are going to release a set of practice problems by Wednesday. There's stuff we want to get in on Wednesday, so you can attack those things. So we'll get you some practice problems, and style's very similar to the last one. Yes? Oh God, there's going to be new stuff like pouring in like you wouldn't believe. It could be, there could be Friday material on the test. Will there be Monday material on the test? Well, we will be teaching new material on Monday, but we got to be a little careful on this. Sometimes somebody asks you to clarify something, and you do it on Monday, but it's really what we call test 2 material. But we're not trying to jam in a lot of material on Monday before the test, okay?
Yeah, in other words, the stuff on Monday will be helpful for the test, even though it's not new stuff. Right?
Yeah, that's kind of how we do that. Yeah. So, the definition was simply that the expected value of x was the summation of x times p of x. And we designate this commonly in statistics with the Greek letter mu. Mu. It is the Greek letter mu, not to be confused with mu. And just to attach it to something that you will always have right, it is, of course, the same pronunciation as the Pokemon Mew. Not Mewtwo, Mew. Mew. Okay, so we got that down. And well, actually, before we do that one, let's just go to our paper for a moment. Let's get back to our paper. Blah blah blah. DocCam. Did you want the other one on the DocCam there too?
Well, yeah.
Okay. So there we go. Let's get that expected value mu, which is the expected value of x, equals the summation of x times p of x. And the summation just is, we could designate this various ways, but simply it's over all values of x, okay? And we only really have to concern ourselves for values of x which take on a probability other than 0, because if it took on a probability of 0, it just goes bye-bye. Okay, so we got that. So what are we going to do? We're going to take 1 times 0.10 plus 2 times 0.20 plus 3 times 0.50 plus 4 times 0.40. Oh my goodness, this could crack my brain here. 0.40 plus 1.50 plus 1.60. And what's that come out to? Yeah, 3 points. Did I make any mistakes in there? Yeah. Oh. Just a sec. Which one? Oh, I wrote that down wrong. Yes. It was 0.2, wasn't it?
Classic copying error.
Classic copying error. 0.2. I was looking at that and I'm going, hey, this is the wrong mean. Thank you. Okay, so let's do that one and fix this little sucker up right here. So that was 2.8. Okay, so it's 2.80. And again, going back to the idea of a balancing point, let's just go to the point view of a balancing point here. Again, think of this as a lever, and you've got a point to balance on a 1, a 2, a 3. Yeah, just a second. I don't like my picture. Let me hide that one for a second. Let's see. What would I do? I got to get it more even like this. I'm going to do it, let's see. How's that? 2, 3, 1, and 4. That's kind of a better lever there. And then the point is I'm going to put weights on that. I'm going to put weights on that, and this is the heaviest weight. On the 3, it gets a 5, so consider me putting a weight of, 0.5 kilograms. And then this one here is going to get 0.2 kilograms, and this one's also a 0.2 kilograms.
Hey, that looks perfectly balanced.
And that is 1 over here is a 0.1.
So if you just look at the 2, 3, 4, it's perfectly symmetric. So the 2, 3, 4 would balance around 3, but then you add in this 1, it's going to shift the balance a little bit towards 1.
It shifts about a little bit.
Just a little.
And so if it, if it didn't have that 1, yeah, it would have been perfectly balanced at the 3, but in fact, it turns out that the balance is going to be at mu equals 2.8. Yes, so that is the balancing spot. Okay, any questions on that? Okay, get the expected value. So really 2 things just kind of to notice today so far is the idea that, it's the sum of the probabilities has to be equal to 1. So if you've got some unknown in there, you can solve for that unknown. And then getting the mean just means summing up the values of x times p of x times the probabilities of each of the values of x. Okay, so in the slide, it says to also find the variance and standard deviation of x. Okay, so we're going to be spending a little more time this week discussing the idea of variance and standard deviation. But the point is that these are a measure of variability here. And we can kind of imagine, looking at our previous slide, that there could have been some situation where the average number of eggs per nest was 2.8, but 1's never occurred, and maybe 4's never occurred, and all of the values were either 2's or 3's. 3's being more common than 2's, so that the average was 2.8. And what we would recognize if we could only get 2's and 3's as opposed to our 1, 2's, 3's, and 4's is that the 2's and 3's, just 2's and 3's would be less variable in our outcomes than when we can get also 1's and 4's. So what we want to have is a way of measuring the variability of the outcomes for the random variable x. And so we need to make another definition here. And we've defined the mean. So we're going to do a general definition first, is that simply the expected value of any function of a discrete random variable. We can get the expected value of that function by taking the values of the function times the values of the function of x times the probability of x. And one that we will see frequently is looking at the expected value of x squared. If you were to square each of the values of x, what would be the expected value of x squared? Well, it's going to be the summation of the x squared times p of x. Okay? And so basically, I'll just give you time to get that down again. You will get these slides posted. But this is a good one to kind of just write down for the moment. Help lock it in. Lock it into the brain. So the thing about the variance, it is a function of the random variable x. The variance of x is simply a function of the random variable x, and it's a very specific function. And so a few things in here. Let me just try to unravel the various equations you're looking at. There's a bunch of things here. First of all, rather than e of x, we'll call it var of x, or sometimes let's just put v of x. But the point is we're looking at the variance. And typically in statistics, this gets designated for a population with the, or theoretical distribution with the symbol sigma squared, okay? So Greek letter sigma with a square on it. And what we see is that this is simply a function of x, okay? X minus mu squared is a function of x. The mean for the distribution will be some constant. And let's ask ourselves, what is that function actually telling us? Well, what it's doing is taking the deviation between each value of x and the mean and squaring those deviations, that deviation, and then saying, what is that average squared deviation about the mean? Now, we can think about the variance in the sense that if the values of x were very close to the mean, then the average squared deviation is going to be smaller than if on average those values of x are further from the mean. And we will illustrate this with further examples as we move along. And since this is, again, just the expected value of a function of x, we can just take the summation of that function, the x minus mu squared, the values of that function, times the probability of x. Now, this here is a derivation here, and this is not an obvious thing as to how we move from here to here, okay? And we're not going to go through that derivation right now unless you want to go through that derivation.
No, I think it's good to know the formulas and have them in your notes, but tell me why. Although it's not so hard, I think it'll be good fun.
Yeah. Okay.
It's bonus from.
Yeah. When we look at the summation of x squared times p of x, we just say, hey, that's just another function of x. X squared is just a function of x. And that simply is the definition of the expected value of x squared. So what you've got here is the expected value of x squared minus mu squared. Or if you want to add one extra line, give me a thing there. We have done that. And if you wanted to, just again, just notice that what you've got is the expected value of x squared minus the expected value of x, the quantity squared. Okay, because mu squared is just the expected value of x. So what is the variance? Well, that might be worth writing out. So what's the variance? It is the average squared deviation of x about its mean. Okay? And that leads us to kind of an interesting thing. It is, why am I looking at the average squared deviation about the mean? Why don't I just look at the average deviation about the mean? That seems like a good idea. How many would like to look at the average deviation about the mean? Anybody good for the average deviation about the mean? So here's something you can do which is fairly simple. You can show that the average deviation about the mean is always 0. Pluses and minuses cancel out. Well, you could take absolute values. Yeah, let's not worry about that right now. Anyhow, we've got the average square deviation about the mean. And so to get it back into original units, which we'll see again in a bit, we take the square root. If we take the square root of the variance, we will come back to the something called the standard deviation. So the standard deviation, sigma, is just the square root of the variance. So the standard deviation is going to be something that you see a lot. You will see this a lot, okay? And just keeping them straight, variance, average squared deviation, and then the standard deviation is the square root of the variance.
Should we calculate it for the problem that we have?
So we should work it out. So let's work it out for this problem. Oops, what a messy sheet. That's a messy sheet. Let's do a nicer sheet. So for our example, you can either calculate sigma squared equals, again, the expected value of x minus mu squared equals, okay, so then you can either take the summation of x minus mu squared times p of x, and you can work this one out, and I'm just going to put the substitutions in at the moment. We could do this. So we could go 1 minus 2.8 squared plus, oops, not plus, I forgot to multiply times my probability. My probability, correct me if I don't remember correctly, 0.10, I think that was, plus 2 minus 2.8 squared times 0.20 plus 3 minus 2.8 squared times 0.50 plus 4 minus 2.8 squared times 0.20, or, and so you can work that one out, or sigma squared equals, well, same as up here, but a common thing to do is do the expected value of x squared minus mu squared, and then you're going to take, to get the expected value of x squared, you're going to take the summation of x squared times p of x minus mu squared. So this part here, you're just going to do 1 times 0.10 plus 2 times 0.20 plus 3 times 0.50 plus 4 times 0.20. Work that sucker out there.
Well, I think that it's going to work out to exactly 2.8 the way it's written. Because there's a mistake.
There's a mistake.
We forgot the little twos.
My squares. I got my little squares on there.
Everybody's favorite little 2 was
missing. The square little 2's were missing, and we got that. And so we'll leave you those to work out. on your own for the next day, we'll just check the value at the start of class. And we'll check the standard deviation too.
Okay, is that it for today?
That's it for today because we are at 20 after.
All right, see everybody on Wednesday.